This is actually going to be a lot of fun. We're talking about quantum now, and quantum sensors are one place where now is actually now. And if you're a Harry Potter fan, it's not just now, it's quantum sensors are your past, your present, and your future. So let's talk about that. My name's Duncan Stewart. I've done some stuff. You can read about it if you care. These other people have done some really interesting stuff, so I want to jump right in. We're going to start by asking Alex, and then Nick, Lily, and Josh a set of testing questions. So my first question is, why do you get up in the morning? And you can use that as an excuse to tell me a little bit about your organization. But perhaps Alex first?
Why do I get up in the morning? We're developing a cutting-edge technology that is making quantum useful. I think for me, that's really the big thing that we're trying to achieve. I'm currently a graduate student, and I'm at the Institute for Quantum Computing. And having worked on this stuff, you kind of see a lot of fascinating physics. And to date, it's been kind of touch and go with the usefulness of it all. But now we're developing a tech that is usable for civilian use cases, but also in defense. And it seems to be such a versatile technology. We develop LiDAR. So it's a 3D imaging device that can also be used for communications, optical communications. So just the sheer versatility of it and making something that is quantum, that is also useful, for me is really exciting.
Thank you. Let's try Nick.
Oh, yeah, so I'm...
And then just a heads up, Lily, and then Joshua.
We should have organized the seating.
That's right. That's perfect. You're in exactly the right place, Nick.
So I lead Quantum Valley Ideas Lab, which is an independent research lab based in Waterloo. And the thing that gets me up is really in the morning is really the mission that we're under. And our mission is really to accelerate commercialization of these technologies. So developing the technology is great, and we spend a lot of time and effort building the sensing technologies, particularly in RF sensing with using Rydberg atoms. But building that technology just for technology's sake isn't that exciting. What's exciting is actually turning it into useful products that can be used across a range of markets. And as everybody can see, RF is everywhere. We can't really see it, but everybody can see that RF's everywhere. Telecom, defense. And so there's lots of opportunities for these technologies to really make an impact in some big markets. And that's really exciting, is the opportunity to make that happen.
Lily.
I think you all heard this morning from David Roeguet about diamond magnetometry. And I've been studying quantum systems in diamond for over 20 years now, so that dates me. What gets me out of bed in the morning is the fact that I get to develop new scientific ideas, new knowledge that's going to have an impact in the real world. I can work on problems that are driven by applications, that are driven by the needs of the industry, and develop the science, the understanding required to push it further. And it's incredibly grounding, both in making sure that what I'm working on is relevant and motivating in seeing the impact in the real world. I'd say the other thing that gets me out of bed in the morning is actually teaching and mentorship. I'm a professor, and helping to develop the next generation of quantum scientists is really important to me. And I think the connection that we are seeing now in quantum technology between fundamental science, applications, and commercialization is incredibly motivating for students as well.
Joshua.
Yeah, so for me, the word quantum attached to the work that I'm doing is relatively new. And so, for most of my career...
You can leave at the side.
Yeah, right, exactly. So for most of my career, what I pursued was operating in extreme environments with really incredible instruments for astrophysics or particle physics. So I started at CERN working on the LHC, and then really found my passion working in astrophysics in places like Antarctica and the South Pole. And when I finished my graduate studies, my expertise was in what we call low-temperature detectors, not quantum sensors. And I wanted to figure out a way to keep doing that. My options were really academia, which didn't quite appeal to me, or go into a traditional kind of tech sector job. And founding a company to take all of the technology that we'd matured through these large-scale TRL-9 scientific instrumentations and commercialize that, for me, was a way to keep doing really cool science work, really cool engineering work at scale in extreme environments.
As a venture investor who hopes Canada might actually succeed one of these days, You made the right choice. So I'd like to, for the audience, I made a joke that quantum sensors are the past, present, and future, but I want to dig on that a little bit. And each of these individuals, extremely experienced and knowledgeable folks, each working on a completely different kind of quantum-enabled sensor. I want to ask them what stage are they at in that technology development and product development. So I'll just bundle a couple of questions, and we'll try the same order of Alex, Nick, Lily, and then Josh, and you'll understand why we're doing it in that order. But the question is, what technology readiness level are you at today? What are you selling? Who's buying? And who's buying today? And who do you think will be buying in the future? So if we could start on that with Alex. Over to you, madam.
Was the second question what we're selling?
What are you selling? The first
What are we
question is, what technology readiness level are you at? What are you selling?
Okay.
Who's buying now? And who do you think will be buying in the future?
Okay, so we're at a technology readiness level of 7. We are making quantum LiDAR, and we're selling the data that the LiDAR produces. The most immediate customers that we're seeing are largely from defense as well as oil and gas, because we're trying to deploy our sensor in the maritime space. So there's a lot of oil and gas infrastructure in the ocean. There's a lot of cables and pipelines. They're also energy sector related. But from a defense perspective, there's a need to do surveillance underwater. Sonar is what's currently used, but it's very conspicuous, so it's loud. It gives away the user. LiDAR isn't loud. No one's looking for LiDAR underwater, so that's kind of an immediate use case. However, in the future, we're also hoping to target outer space. We're hoping to bring our LiDAR down to the size of a chip, in which case it could go into consumer products, consumer electronics. And we see the potential for it there. But in the immediate short term, it would be in the underwater space for defense as well as oil and gas.
Can I call you on that a little bit and ask you to go deeper? Who's actually giving you money right now?
Defense and oil and gas.
And that's a research deliverable, or it's a product? It's a prototype product, or it's a shipping out the door 10 of these a month?
Prototype.
Prototype. Mm-hmm. So defense, R&D, building prototypes. Okay, thank you. So maybe we can go to Nick.
Sure. So we have multiple projects active in the lab at different stages of technology readiness. The first project was to develop and commercialize these Rydberg Atom RF sensors.
I can see that atom from here.
And so they're in the process of, so we've actually created a spin-out company to commercialize that. So I'd say that first project is really going past TRL7. They have an alpha product. We have a version of it in the booth if you want to see it. And they're making good progress to sell that into 2 sort of main markets. One is 5G telecom network operators. So you can envision every Bell or Telus technician having one of these systems to measure and operate, characterize, and evaluate the performance of a 5G network. The second area is the sensors have a lot of capability that are relevant for spectrum monitoring. So that clearly tends towards RF spectrum situational awareness or spectrum intelligence in the defense space. So think of electronic warfare, electronic support measures. And so those are sort of the 2 main initial product areas that our spin-out is chasing. We have a second project on turning that sensor into a radar receiver. And that project is probably
a radar receiver.
Radar receiver. So, so it drives up sensitivity and has the potential to be used again in defense or weather forecasting or potentially space-based SAR type synthetic aperture radar use cases. That's probably the components are, I would say, at 7. We've tested them and built them. The radar system is not at 7 yet. So that's the next phase of our development in the lab, is to get it to a complete working multi-static radar system that could then be deployed in a multiple potential use cases.
Who's paying you right now, and how much are they paying you?
So we've had economic development funding from FedDev Ontario, MedCat, and then we've had sponsor donations from the Mike Lazaridis and Doug Fragan foundations. We have had about 30% of my revenue comes from contracts, so NRC Quantum Sensing Program, DRDC Ideas, DRDC Micronets, ISC Challenge, significant funding from DARPA in the US, so a good chunk of funding from multiple projects with DARPA, and now we're branching out to do some work funded by some of the NATO S&T work on RF sensing in defense.
So just for the audience, you obviously caught it. Early stage quantum development, a lot of public sector engagement in funding that technology development, okay? Lily.
So I'm an academic, but I had the privilege last year of working closely with SB Quantum. And you heard a little bit earlier today, again from David Roy-Gay, about some of the markets that they've been working in. Now, I'm a little worried that David's going to tell me I'm wrong when I say this, but if I was going to estimate, I would say that their magnetometer is at TRL stage 8, with pushing towards 9, because it's going to be deployed as part of the MagQuest challenge to actually help refine the world magnetic model. So that's a real-world, in-space use case that they should be launched sometime this year. So let's see, TRL level, now product, magnetometry. Now, the diamond technology that I've been working with can be used for the kinds of products that SB Quantum is producing to measure vector magnetic fields like the Earth's magnetic field. And that, as a technology, has many applications. And I would say the product that's being sold is not necessarily the magnetometer, but the solution to the specific problem that it's tackling. And so depending on what sector you're in, it might look like a very different system that's being sold. I'd also mention that the same underlying technology has many other use cases. So for example, diamond magnetometers could be used to improve NMR, which would allow us to identify the structure of materials, of molecules, for example, trace gas sensing or material development. So the TRL level for a given technology isn't necessarily one number. It can depend on the application sector that you're looking at. Now, in terms of who is buying diamond magnetometers, oh dear, again, I'm not the CEO of SB Quantum, so I hope I don't misspeak here, but a lot of the support has again been coming from government. So for example, they have contracts with the European Space Agency. The MagQuest Challenge was again a government endeavor with support from NASA. And they're building out into the commercial sector at this TRL 8 level. And where it's going is hopefully to then reach the public through this type of security product that they're developing now to be able to detect magnetic anomalies.
Joshua, we're going to go to you, and I'm going to throw in an audience question, which is what defines a sensor as a quantum sensor? Close to your heart. I know you can handle it.
Okay, so fundamentally, I'm going to hit that at the end.
Yeah, let's save that at the end.
So fundamentally, what T0 technology is doing is taking a set of established tools that are very mature and in the field and being used every day in astro and particle physics, and adapting them for industrial, commercial, or government use cases. So the technology itself is TRL9. And that's true over a wide variety of use cases, sensing paradigms, whether we're looking at X-rays, UV, microwave, whether we're photon counting or imaging, whether we're doing spectroscopy. All of these are mature systems that have been used for well over a decade now. T0 itself supplies an aspect of that for scientists that are using it every day, which is our commercial product for our readout and control electronics. And to date, the sales of that have been enough to keep the company profitable and growing for this segment. And so our customers are people like JPL, universities, scientific experiments, radio instrumentation, et cetera. Separately from that, T0 as an organization is undertaking R&D to generate a commercial supply chain to fully integrate these end-to-end instruments ourselves. And the idea is we'll have an instrument like a telescope, but we're going to be using it for space traffic management. We have an instrument like an MRI, but it's using quantum sensors to do medical imaging. This effort is R&D fundamentally, and we benefit hugely from economic development funds from Quebec government and through Innovative Solutions Canada in testing elements of that.
Do you have any commercial customers?
Yeah, for the elements of our system, which are primarily our readout and electronics product, our our customers are JPL in the U.S., about half a dozen other research labs, defense labs, and government labs. Yeah, and then your question of what is a quantum sensor? So I would define a quantum sensor in this case, and these are all superconducting quantum sensors, as they require superconductivity to work. So this is one of the focal planes that's used at the South Pole Telescope. This is not a T0 technology focal plane. This is an academic research sensor array, but it was deployed in 2017, so nearly 10 years ago, and has been taking data ever since. Yeah.
Okay, perfect. So quick recap there. TRL 7, 8, 9, technology that is still being funded by mostly public research and I would call technology development efforts, going all the way to technology that has already been in operation for more than 10 years or 20 years. So, and the idea that a quantum sensor is incremental, even Alex said, when I have paying customers, they're going to buy the data. They're not actually going to buy the quantum sensor. So there are users of sensing data all over the world, whether it is LiDAR, whether it is RF, whether it is magnetic fields, or whether it is high sensitivity photon counting, I guess, if that's fair. And there are use cases all over the world. Those use cases exist right now. There are sensors filling those roles right now. What we have before you are 4 people that are building the next generation of those sensors. So I want to now pivot, and anybody can answer this, that what has surprised you the most in the quantum sensor space? You've been operating in it, it's your life, it's what gets you up in the morning. What has surprised you the most?
I can start. What surprised me most, coming from an academic background, if you read the scientific papers on quantum sensors, you're going to see so much emphasis on sensitivity. What is the smallest change that you can measure? And looking in the real world, coming into applications, what you find out is actually sensitivity is often not the most important thing. And what quantum sensors can offer is not just sensitivity, but also things like stability, accuracy. If your sensor is based on a fundamental constant like the electron geomagnetic ratio, that's not going to drift with time. It doesn't need to be recalibrated. And so there's capabilities beyond just excellent sensitivity that are offered in the quantum space.
I'll take this one. So coming from an astrophysics background, similar to this question of sensitivity, we're always trying to squeeze the most performance out of our sensors. And what's been surprising in this commercialization push is understanding that for a lot of the use cases we study for industry, especially for defense, actually the sensors can be much less performant and still head and shoulders above anything that currently competes with it.
Sorry, the new quantum sensor does not need to hit the exquisite performance limit that you can probably drive it to actually make a significant difference.
That's right. And so our main challenge isn't making a better detector or doing the technology development to make an even fancier one of these. It's a much more meat and potatoes challenge of assembling the supply chain, integrating a system in a commercial way that serves an application that is a non-science application, working with stakeholders to actually understand what they want, and then most importantly, assembling the funding to be able to buy a first article, since these are actually quite expensive devices.
Yes, and they've been around for a while because they were invented when I was a graduate student, which was a very long time ago.
No comment.
Nick and Alex?
So I think one of the things that we've seen is to actually render these into useful things, it is really a team sport. Like there is no one researcher who's going to do all the things we need to do, or one scientist or one engineer. It very much requires...
I just have a question. Did the scientists tell you that?
Well, I think we find when we hire people, we have to sort of recondition people to really move out of sort of a self-directed kind of idea to working as part of a cross-functional team. And we might have people engineering these sensors, material scientists, real expert artisanal fabrication people, having to work with quantum optics people to figure out how to drive those sensors well, and then figure out with some FPGA skilled programming people to actually take the data that comes out of the sensor and do something useful with it. And then finally we have packaging people that have to kind of think about how that renders into, like, it can't be an 8x8 cube that you're giving somebody as a product. So all those the team has to come together to actually deliver on this, right? And I think that's a critical part of trying to move this industry forward, is thinking about how some of those areas are also problems that, like Lilian said, are not all about pure performance. They're about doing some of the things that people may not want to work on, but are critical to actually make it useful.
Alex, what surprised you?
What surprised me most is rather the willingness of industry to actually engage with this quantum technology, because there's a bit of a reticence from the part of industry to adapt quantum technologies. The sort of word quantum is a little bit scary. But when it comes to sensors, people are really creative in the ways that they think of to use them. They'll sit down with you and they say, can it do this? Can it do that? And from the government's end, the Canadian government has fostered this ecosystem that is really allowing us to build these technologies in a safe environment for us as businesses, as startups. So that has been pleasantly surprising as well.
I like your positive take on the Canadian government, which I'm part of. We'll leave it there. What is quantum hype and what's quantum reality?
Quantum hype is when a publicist takes a groundbreaking scientific experiment and extrapolates to what could be possible without taking into account all the compromises that were necessary to make that groundbreaking experiment. And often what is difficult is not showing that you can get this incredible figure for sensitivity or this incredible figure for accuracy, but also doing it with all the extra components that Nick was just talking about, with the size, weight, and power that's appropriate, with the refresh rate that you need, and not taking into account those externalities and extrapolating possible performance. That is quantum hype.
Yeah, I'll take the controversial take here that for sensing, there's not, the concern that we have in terms of overhyping quantum technologies hasn't quite made it into a large part of the sensing field, in part because a lot of us have been grinding away on sensing challenges before we had this umbrella of quantum to put it all in. And so there's not the sense that, like, tomorrow a technology is turned on and it's going to revolutionize quantum sensing, because most people think about RF sensing or millimeter sensing or biomedical imaging as these separate siloed things. And so I find many people are surprised to hear of the extreme capabilities that exist today in these systems, primarily in the sciences. And if anything, there's much less hyperbole among quantum sensing than I would have expected, given our overall fear of hype in the quantum world.
You're saying we need more quantum hype?
I'm hard-pressed to say that, but it is certainly the sentiment.
Alex or Nick? Question is, what's quantum hype and what's quantum reality for you?
I tend to agree with what Joshua said. These are really capable technologies, and it's important to let people know what they can do.
I think I agree that the hype is not as big in sensing, because I think when you look at sensing, as Joshua said, there's lots of these sensing markets, and there's lots of quantum technology platforms, and that sort of mapping of what each of these platforms could do in a specific sensing market is kind of being developed. I think the reality is, because there's all these markets, and those markets exist today. People buy gyroscopes today. People buy magnetometers today. People buy these things today, and they have known with data sheets. So it's not like you can hype, because if you create a quantum sensor, you better produce a data sheet that shows where it's better. And what better is I think relative. Could be it does something at lower power, it has a unique capability because it's based on atoms, what have you. But the reality is you better show up with better and have the characterization and the proof that that sensor is going to be better. And then I think you have something, because people buy $10 billion worth of gyroscopes. If you get a better one, you're likely to be able to sell some.
Can I
Go ahead,
push
yeah,
back
jump in.
a little bit?
Yeah, and if anyone on the panel has like a concrete example of
Yeah.
Yeah,
Okay.
let's do it.
So in diamond magnetometers, there have been some really beautiful recent experiments showing that you can measure fields measured in femtotesla per root hertz, and that probably doesn't mean much. I know I'm not supposed to be technical.
Femtotesla per root hertz.
Yeah, that means you can measure potentially the magnetic fields produced by your brain while you think. And so there are proposals out there to create a brain-machine interface by wearing diamond magnetometers that are, and it's really nice, diamond's super small, this could be really lightweight, we could all walk around interacting with AI nonstop.
Sounds expensive, but beautiful.
But when you think about what it took to achieve that experiment where they had that level of sensitivity, it was a room full of optical equipment. And a lot of the compromises they had to make to reach that sensitivity aren't necessarily something you can scale down. You need 12 watts of laser power. Do you really want to have 100 of those attached to your head? So that's not to say it can't be done, but the experiments we have aren't yet at the point where you can really predict that trajectory without significant additional scientific breakthroughs. On the other hand, I'd say quantum reality is that there are a lot of companies that are making prototypes and going out and testing them in the real world. And quantum sensing is happening now. SB Quantum makes their prototype and they take it to the geomagnetic lab at Natural Resources Canada and test it in the real world. And they map out the accuracy using state-of-the-art facilities so that they can say, okay, this is exactly how it's performing. We can create a spec sheet, as Nick was saying. And so there is both hype and reality in the quantum sensing space, but probably a little bit more reality than maybe in the quantum computing and cryptography areas.
Can I double-click Nick, Alex, or Joshua on the specs that we need to hit, which are actually driven by the customer, by a real customer in a real market, as opposed to what Lilian was saying as, hey, I have this quantum sensor that can do this better than anything else. Do you have a concrete example where you've run into that?
Yeah, I think we crave that sort of requirements discussion with end users, because then you've got goalposts to take. And we have some examples, we have good examples of that, where we worked with a European satellite company and with NRC and DLR in a collaboration to basically say, here's kind of what our RF system looks like on a satellite today. Can you do this, right? And can you do something that's got a similar performance capability with a lower size, weight, and power, with the right thermals and dynamics, and we didn't space qualify it, we're not there yet, but it becomes a real sort of set of user requirements to say, here's a challenge, can you meet this? And I think it was, and from the LiDAR perspective, I think you said the same thing, right? Like, those challenges, or people share their problem statements, and I think that's the biggest thing in this interaction with industry, is to get those problems out on the table, and then I think the creative quantum sensing companies will tackle those.
Joshua, you said you had to actually dumb down one of your sensors to get it,
Yeah.
to make it useful.
Well, I would say, I was going to go a slightly different direction with this.
That's the wrong description, but please.
Which is, for the systems that we're most interested in promoting into industrial or defense or government uses, there are two, maybe 2.5 critical technologies. And those 2 to 2.5 critical technologies are things that we're expert in. And for scientific end users, that's enough. We make the data sheet around one or both of those, and that's what they want to buy.
What are those, you're talking about your 2 critical?
Yeah, exactly. Well, the 2 critical technologies for that whole end-to-end system. And scientific users will just take that one piece and be like, that's perfect. That's what I want. It slides into this system. You're the best vendor. I love your data sheet. We're done. When you're talking about trying to find end-to-end use cases with government agencies or non-scientific applications, the requirements are much less stringent typically, but the challenge is they don't want those 2 critical technology elements, they want the whole thing. And so in order to actually successfully commercialize it, we as an organization have to put together all of these other pieces that are not necessarily technologically groundbreaking. They're cryogenics and optics and data crunching and image making, and all of this stuff has solved problems, but it's expensive and it's time consuming, and this is some of the main challenge for us.
You're saying you might have to build a company.
Yeah, exactly. Yeah.
And
Might
sell
have to build
and sell product.
Might have to build a company,
customers.
and the idea that the entire thing end to end has to be assembled before you can real world use case it.
Right.
And that means that's a lot of investment to make something that is tailored for that real world use case before it can be deployed. And it helps to have strong signals from those end users that that development is going in the right direction early. So this is one reason why we care a lot about the Innovative Solutions Canada testing stream. Like, it's one of the very few examples where we get to work with an end user like early in the stream as we're building those slots, like as we're putting the whole system together.
Right. We won't talk about whether that funding was increased or decreased last year. Alex, was there something on your side for, you mentioned before that, in fact, when you were talking to your end users, they only cared about the data, not how it was being acquired. How did you do that translation?
I wouldn't say that the customers necessarily came and said they only care about the data. It was more a question of scalability from a business perspective. We make hardware, and we make very sophisticated hardware that is also very expensive. So we came to the conclusion that if we just sold hardware pieces, we wouldn't be able to build like a startup, like a scalable, fast-growing business. So we sat down and took a thought as to, with the hardware that we have, what can we actually provide to the customer that's useful to them, but also allows us to build kind of a sustainable, scalable business? And the answer is to sell the data that the sensors produce. And it turned out that that was a feasible thing to do. Initially, we had some roadblocks because we are making LiDAR. We want to go in the maritime space. And that meant that there was a gatekeeper, and that was the UUV, like the underwater vehicle and robot providers. They want to sell the data because it's such a good business. So they tell you, we'll buy your hardware, but we will sell the data. So then we kind of had to figure out, okay, how do we get our sensors in the water without having to just sell the hardware to the UUV providers? And we decided to make a network of floating surface vessels, buoys, and other vehicles that would be able to kind of survey infrastructure and go out there and do their own thing and move around. So these are off-the-shelf components that we're buying and putting together, but that's how we kind of got to the data model. It wasn't so much that the customer said, we don't want to talk to you about hardware. It was, we need the imaging. We're willing to buy the data because that's what we need. How can you get that to us?
I like that. Customers that actually have needs and are willing to express them and then have them being met by a quantum company. Who knew? What keeps you folks up at night?
I can go first on this one. Yeah, like I worry about competition and pace. Are we going fast enough? Can we get where we need to go fast enough? Can we get to, you know, our spin-out companies? Can they get to a point where they're successful with multiple users and multiple products in the market? And I think that keeps me up. And I worry in that terms of the competition, that our competition's getting more funding and more nourishment for it to grow faster than we can in the research, and or grow faster than our startups can grow. And that makes it harder to kind of be the first with a good thing in some of these markets.
Okay, that goes back to, we're talking about a deep technology. It takes more time and more money to get it to market.
Yeah.
If you don't have an early adopter of some kind that's willing to pay you something, you're at a disadvantage.
Right.
Yeah.
Sure. I think your question was implicitly designed to be what keeps you up at night because it's a bad thing. I do have two answers, and one of them is the other way around, though, which is...
We can start with the bad and then pivot to the good?
Oh, yeah, okay, sure.
You want to go good and then bad?
Not once you put it that way. Yeah, so, okay, one of the scary things...
Harry Potter had a bad side, just so we're all clear.
One of the scary things right now is, in order to build large end-to-end systems that will validate some of the most effective use cases that we're pursuing, our first customers are likely government and defense customers.
Right.
And we rely on being able to predict and trust that programs that fund that exist and will continue to exist, or procurements that go through or contracts that are written will continue to exist. And one of the key challenges right now is procurement timelines through government agencies in Canada are extremely long. And last year, there was a funding issue with the Innovative Solutions Canada program in which contracts that were quite close to being completed, or in some cases completed, were wiped out. And that kind of uncertainty is terrifying when it comes to trying to put something together that requires, thinking 1 or 2 years into the future in terms of scaling up the people working on a project, scaling up the cost investment. So as we're making these kind of larger bets as to putting together a complete system together for medical imaging or for space situational awareness demonstration, that's a big bet that we're relying on some consistency. On the other hand, I do think that in some ways what we're building in terms of having new access to the unseen world is very similar to having a microscope for the first time. And so, when you ask, who are my customers, I can tell you who I think our first users are. And I can tell you who is currently using that technology in the confined space where it exists. But I have to admit that once these become accessible, there's going to be use cases we have not thought of when it comes to being able to image in frequencies and colors that nobody has taken pictures of right now. There are going to be use cases in microscopy and remote sensing. There's going to be use cases in terms of material determination from spectroscopy. And that is only going to happen once we have demos that are accessible to people where they can take it and start pointing at things.
And just to double click on that, the single photon sensitivity at the scale of a megapixel camera, which did not exist 10 years ago, and now I can buy from you or someone else?
A megapixel camera, I think most of the field agrees might exist by the end of the decade.
Okay.
Today, non-commercial cameras are 60,000 pixels or so.
Okay.
And to date, we're working on our first commercial camera. And it will not be 60,000 pixels, but it probably won't be too far off.
That's crazy. What keeps you up, Alex?
I guess if the question is what really worries me.
Exactly. Yep.
It's a very similar answer to yours and yours. Those are very grounded answers. What literally keeps me up is the sheer amount of work that a co-founder has to do. Putting together presentations.
We have to convince some of the people in the audience to start their businesses. Don't forget that.
Okay.
Part of our mission.
No, I think you're correct. It's the continuity of the funding that we rely on to do what we do.
Yep. Startups are in a tough space here. And for me as a physicist now turned to the dark side, literally, and as a venture capitalist, the challenge I see again and again is how do I invest in a company when the signals of company success are so far in the future? And that requires the ability to take on risk. It's supposed to be called capital de risque. But the fact is there's not just market risk here, there's very high technology risk. It may not work, or it may take quite a lot longer before it does work.
And that actually is related to what keeps me up at night.
Okay, what is it?
Because I'm at the academic sort of low TRL level, and I'm thinking about where is this field going to be in 5 or 10 years, not what can we sell today. And what keeps me up at night is what haven't I thought of? As we push this technology forward, what is going to be happening in the material? What charge dynamics? What other types of defects do I need to consider that I haven't thought of yet that's going to be the limit that I haven't included in my estimates? And the other thing that keeps me up at night is that for every obstacle that we find like that, there's going to be a solution, and it's really fun to think about them, and it keeps me up until early hours of the morning. So it's kind of a flip side that there are going to be obstacles. You don't know if it's going to work, but you also don't know what breakthroughs are going to happen. And I'm continually surprised by things working that I never dreamt could be possible.
We had a couple of questions from the audience that have said, hey, wait a minute, you folks on that esteemed panel are presenting a very different picture. I thought quantum was 2030 or 2035. Why is quantum sensing different from quantum computing?
One difference is that quantum sensing is not as clearly defined. The difference between classical sensors and quantum sensors, it's not as clear-cut as the difference between working with bits and qubits. And as a result, when we talk about a quantum sensor, we can be including things that we've been working with for decades. I mean, the first atomic clocks, the first atomic magnetometers, those are technologies from the 50s. They've been around for a really long time. Of course, they've been refined. They've been getting better and better and better. But there's a huge variety of quantum technologies that I should say, technologies that have been enabled by our understanding of quantum mechanics. And in my mind, that's what a quantum technology is, a huge variety of sensors that have been enabled by our understanding of quantum mechanics. And this is a very big difference from what we have with quantum computing, where it's more of a monolithic idea.
Okay, just because we have 5 minutes left and I want to stay on message, my personal goal is to get at least 3 people in the audience to commit to a new startup. And what could we say that would motivate these people to say, hey guys and gals, in this quantum sensing field, actually, yes, driving a startup is going to be brutal and your mother will think you're crazy and you will get lots of no's, but it's actually it's a great place to be at this time. Why is that?
So I think for many people in this space who would be founding companies in quantum sensing, these are technical founders. And one of the big challenges is coming up in academia, instrumentation, and research, having to choose between continuing to do that kind of R&D, build great things, work with fantastic people, doing the field that you just dedicated a PhD of your life to doing, or leave and do something entirely different in industry, in some other field. And one of the revelations for me was being like, is there a third way? Is there a way that I can do what I'm doing right now, but better resourced, bigger ambitions, faster, different team, and take the right combination of things that I like about industry and the things that I like about academia? And if you're working in quantum sensing, you're in a very privileged position where what you're doing has industrial applications. It actually is possible to build a research-oriented startup that continues having an impact academically while also building real innovations that matter to people.
Quick shout out to the quantum computing people because I know they're going to come after us, so we better say nice things. I see Photonics and Xanadu and Nord all publishing papers at the top of their game in the world at the same time as they're leading the quantum computing effort globally. Sorry, Nick.
I was just going to comment on Joshua's comment, right? So in some ways, our approach is a bit of a way to achieve what you just described, but achieve it in a different way as a focused research lab organization where the focus is on applied research and development and the commercialization of these technologies, right? And why can we do it? What's the goal of trying to do it? Like our mission is like a 3 to 5 year project with a team of 7 to 10 people with an investment with the lab and the infrastructure and go from, for a person who's got a good idea, take that idea towards fruition to, I would call it a commercial ready prototype of the technology. So like, I think, there are ways to achieve that, in environments that aren't as academically tied, and we're trying to sort of create a model that does that. So.
I remember fighting with other grad students at Stanford for access to the dilution fridge, and then I went to HP and someone said, oh, do you need 2 of those? Because I'm willing to share. Alex, your journey as a founder, how would you encourage someone else to follow you?
Okay, when I was doing my master's degree, I had a supervisor named Professor Norbert Lutkenhaus, who is now the director of Institute for Quantum Computing. He was the founder of a company called Evolution Q, and I was seeking advice from him because I wanted to do a startup, and he said timing matters. It's the #1 thing that matters. Everything comes after that. And I think the timing is right. There's enough momentum. People know enough about the technology to be interested and to engage with you, but it's also new enough that whatever innovations we have make a big difference. So to do something with quantum, in terms of timing, the timing is now.
I don't think we can top that. Let's thank the panelists. Quantum Now, you just heard it right here. Don't forget.